Welcome back to the next video in sequence here, talking about logic, set theory, and inference. I wanted to provide some extra material for people that might not have had already a full bachelor's degree in computer science. Maybe you're taking this as part of a master's degree, you already have a STEM background, but maybe you haven't been programming for a long time. If you're already a professional programmer, I would encourage actually not watching this video. It's better to try to puzzle it all out yourself. And in fact, even if you feel like you are likely to need some extra help, if you do have the ability to get started trying some things, I would again encourage you to do that. But if you're really stuck, if you just don't know where to begin, my hope is that this video will give you enough of the material that you need to be successful coding up the MIU problem that I introduced in the previous video. So again, don't watch it if you don't have to, but if you need it and there's too big a leap to getting started on this project, hopefully this will give you a leg up. It'll get you past that first step. So we have this very interesting problem, I think, where we have 4 rules that can apply, transforming strings into other strings. 2 of them yield more than one output, possibly at a time. There are different ways to apply those rules. Each output of a rule operation is itself a new string. And we also need to track how each of our strings was created. We're creating a derivation. We're creating an explanation of how we got from the starting point to the finish point. So we've got to figure out how to accomplish that. And if you're working in an object-oriented language like Java or to an extent Python, as well as many other languages, C++ and so on, you'll have access to these structures called classes. If you don't have an object-oriented language, you can still do some of this in a similar way. You can, in C, you could use structs, for example. So there is always a way to do this. But here I will just assume that you're working in an object-oriented language, since most people today, it seems, are writing in Java or Python or maybe something like Rust that's a bit newer. So I think one way to approach this problem is to think of it as needing 2 fundamental classes. We have steps in transformations in which we want to be able to record that we have a string and a particular rule was used to derive that string from a previous string. And because we have many of these steps, we have to have some kind of a structure that gives us a full derivation that goes from the start to the finish and tells us each transformation step, each rule that we applied, and what string resulted from that application. So it's an ordered list that does need to keep an order, and we're also going to need to be sure to have a data structure that gives us access to the last step, because we're always going to be working on the last step in this derivation. So what does this look like? Here again we have our 4 rules, and for this example I'll be looking at just the first problem that we've been given, which is to derive MUIU. All right, so we start with MI. We've been told already for this system all strings must begin with MI. All derivations must start with the sequence of 2 letters MI. And we can think of this as being a very simple derivation already. It's a derivation that doesn't result from applying any one of the rules. It's sort of a rule 0, and the string is just MI. So we have a list of steps in our derivation, and we have only one step. It has no predecessors. It's the first step, and it's the result just given. It isn't the result of applying a particular rule. The first thing we do is we go through all of our rules on this one string that we have to see what other strings we can produce. We produce MIU by applying rule 1, and we produce MII by applying rule 4. And if we look at these in terms of the data structure, we have now 2 derivations that each have 2 steps. The original MI, step 0, and then we have a new step that is the result of applying rule 1 to yield MIU and rule 4 to yield MII. So we have two derivations, each of which has two step objects inside it. And here I've used square brackets. If you're working in Python, well, your derivation can just have a single variable inside that class, which is a list. It's probably the easiest thing to use to get started, and lists are ordered. Right, so we go on to the next step. Now we've got two strings that we can cycle through, checking to see which rules apply. For MIU, only rule 4 applies, so we get MIU-IU. And then for MII, we have two different rules that can apply, one to yield MIIU and the other to yield MIII. Each one of these three results now, again, has a derivation. The first one is from MI, then applying rule 1 to MIU, applying rule 4 to get MIU-IU. So we're building this set of derivations, and at each step, each time that we run through all of our strings, we're getting more and more of these derivations. This is a critical feature of this algorithm. It expands over time. We get more and more options. And we might call each of these iterations through all of our current strings an epoch. So borrowing sort of from machine learning terminology, epoch is a kind of a time period. So in a given time period, we're looking at all of the rules that apply to all of our current strings. And we're just looking again at the last step in a derivation of any given string to see what can we do next. Right, so at epoch 2, we now have three derivations. There are three possibilities that we can wind up with after we try all the rules for every string that we have. And here you can just see what the data structure would look like. Hopefully at this point you're getting an idea of the pattern and have an idea of how to actually go and implement these data structures in your chosen language. We get down to epoch 3, well, we've branched again. We start to get a little more complexity and variety. We can actually apply rule number 2 now. And rule number 2 can apply in two different ways. We can either take the first three i's of M-I-I-I-I, M with 4 i's. We can take either the first three i's and replace it with a U, or we can take the last three i's and replace it with a U. So here we have our first case of where rules 2 and 3, which can generate multiple options, actually do so. Rules 1 and 4 always just have one way in which they apply, because they just apply to the end of the string, essentially. All right, so now we have 5 different derivations. And finally, with one more step, I'm not going to go through all the derivation for all of the possibilities. We can just look at what's the one that gets us the answer. Well, it's looking at MIIU, and applying rule 2 to replace those first three i's with a U, we get MU-IU. All right, and that's our answer. So that's another critical feature of this algorithm. You've got to know when to stop. So every time you generate a new string, you need to check to see whether it's gotten you to the target, to the goal. And if you have, then there's no point in deriving any more strings. You can just stop, and you're already looking at that object. You're looking at that derivation, and so you can just go ahead and print it out, report the answer and the derivation. So here's what the data structure for that option would look like at last. Right, and that's all there is to it. So give this a try. Hopefully this gives you an intuition about how to get started, gives you the concrete data structures you need, and see if you can make it happen. Good luck.